A dangerous asteroid is heading towards Earth. It's the size of the Empire State Building, and it's traveling at 16,000 miles an hour. It's called Apophis, after the Egyptian god of chaos. It will fly close to us in 2029. It won't hit us this time, but when it returns in 2068, that could be another story. If it blows up over a city, millions of people will die.
This could be the most devastating single event in U.S. history.
Earth is stuck in the crosshairs of a potential asteroid strike. Apophis is one of around 2,000 potentially hazardous asteroids that present a real and present danger. Asteroids have hit us before, and they will hit us again.
As far as cosmic dangers go, they're number one on the list.
This is not a drill. If we do nothing, this is our future. December 2018. The U.S. military detect a huge explosion in the Earth's atmosphere, high over the Bering Sea, off the coast of Alaska.
When an explosion of this magnitude is detected, everyone's mind goes to the same thing, nukes. But when the real answer was found, and it was determined that it didn't even originate from Earth, that was even more shocking.
The cause of the blast? An asteroid.
This asteroid was 30 feet across, something like that, over 1,000 tons. But it was moving at 20 miles per second, over 70,000 miles an hour.
This asteroid was small, and it exploded in the atmosphere over the ocean, so nobody was hurt.
But if it had been bigger, or it had come in over a different place, or it had been moving a lot faster, this could have been a dangerous object. But the scariest thing about it is that we didn't see it coming.
So far, we've been lucky. But near misses happen all the time.
About once a year, we get something the equivalent of a nuclear bomb going off in our atmosphere. And while that sounds horrible, most of these happen tens of miles up over open ocean where we go on completely oblivious.
We may be oblivious to most of the threats from space, but they are very real. We're going to get hit.
Over a certain amount of time, an asteroid impact is inevitable. It will happen, 100% absolute certainty.
NASA considers the threat from the skies so severe, it has made protection from asteroids a top priority.
These events are not rare. They happen. And of course, it's up to us to make sure that we are detecting and characterizing, tracking all of the near-Earth objects that potentially could be a threat. This is not about Hollywood. It's not about movies. This is about ultimately protecting the only planet we know right now to host life, and that is the planet Earth.
To help plan protecting our home, we carry out Earth defense simulations. For 3 days, 200 scientists at the Planetary Defense Conference battle a simulated asteroid 20 times larger than the Bering Sea space rock.
We practice, all right, what if this hits a major city? What would we need to do?
By running potential impact scenarios, we can prepare for a real asteroid strike.
This is like a fire drill that you would do at school or at work, where you practice and think about, okay, what if? Where are the exits? How do I get out? How fast do I get out?
The drill starts with the discovery of a simulated Earth-bound asteroid.
So the first information is there's a big asteroid coming towards the Earth. Then we get a better estimate of how big it is, how fast it's going, and where it's going to hit.
The asteroid is heading straight for Earth, with Denver, Colorado in its sights. The planetary defense scientists send up a simulated spacecraft to smash into the asteroid and push it off its path. But it's a big gamble.
You can push it the wrong way. You can potentially have unintended consequences.
In the simulation, the spacecraft strikes the asteroid, deflecting it away from Earth. But the impact dislodges a 200-foot chunk, which is now heading straight towards the eastern seaboard.
So there's this one last piece that is now going to hit New York. We know that something that size is going to have citywide consequences. That is huge. That's a horrible impact.
When you're actually in the conference room and you understand eventually that New York City is going to be destroyed, and you're having strategies about how to evacuate people, all the timing, when you're doing the simulation, you're in your head, you're thinking about these things, you're trying to reason them out. But can you imagine the feeling in your gut, right, in your heart, if this was real?
If this were real, the chunk of asteroid would strike Earth's atmosphere at 43,000 miles an hour. As the space rock hurtles down, it collides with molecules in the atmosphere, which buffet the falling rock.
It's kind of like doing a belly flop into a pool, right? You're going from the vacuum of space into the dense lower atmosphere in mere seconds. And that's an incredible amount of pressure to put on the object.
The asteroid slams into the air ahead of it, compressing it violently. The surface of the asteroid gets hotter and brighter.
It's actually the air itself that's glowing luminously from the heating of the shock wave, the world's most intense sonic boom, if you will, that heats the air to incandescence as the object passes through. So that's the source of that brilliant illumination.
This bright burning asteroid is called a bolide. We witnessed one descending over the Russian city of Chelyabinsk in 2013.
All of a sudden, there was a huge fireball streaking through the sky, and people had no idea what they were witnessing because it looked like the sky was on fire. It was insanity.
As the asteroid descends, the compression of the denser air beneath it starts to flatten and even disrupt the falling rock.
There's a high pressure on the front, there's no pressure on the back, and it's being superheated.
And that intense temperature causes the air to glow, which is how we see the streak of a meteor. And it also disintegrates the asteroid itself. It's hot enough to literally melt rock.
This can often lead to them exploding.
The combination of heat and pressure invade the falling asteroid, causing it to blow up.
Most asteroids don't reach the ground before they completely disintegrate in a tremendous release of energy.
This is what we call an airburst, and we learned a lot about these while we were testing nuclear weapons after World War II. Some of these bombs were blown up underground and on the ground, but they found out when they blew up bombs above the ground, it actually did more damage. It was more widespread damage.
The explosion of the Chelyabinsk asteroid sent out a powerful shockwave at thousands of miles an hour. The blast traveled over 100 miles. It damaged 7,000 buildings and put 1,500 people in the hospital.
All of the injuries pretty much came from people who saw, oh, what's that bright flash in the sky? And they came close to a window to look and see what it was, and then the pressure wave hit and blew glass in their face.
The Chelyabinsk asteroid was only 65 feet across. The rock in the defense simulation is 3 times more massive, and it's heading straight for New York City.
Imagine what would happen if an explosion 1,000 times greater than that over Hiroshima hit New York. We're talking about an utter, complete destruction of the city and millions of people.
With so little warning, the only option would be to evacuate New York City.
How do we get everybody out of New York City within just a few days? That's where panic sets in. That's where fear would really become the dominant emotion.
Anyone left in New York City would see the bolide racing in, followed by a blinding light as the asteroid explodes above the city. The blast would be equivalent to the largest nuclear weapon ever detonated on Earth.
Buildings would be flattened, melted. There would be fires for miles around. In the first moments of the explosion, 1 million people could be killed instantly, and many more would die later in the rubble and the ruins of what would happen there.
Everything within 9 miles of the blast epicenter would be completely destroyed. The intense heat and pressure would wreck buildings.
It's the worst possible day for New Yorkers. And not just the city itself, there's something like 15 million people living in the New York area.
The shock wave would race out over 250 square miles.
This would certainly be the worst disaster that the U.S. has ever experienced. We're talking about millions and millions of people displaced, affected within an instant.
This scenario is just a simulation for now. The asteroid Apophis is heading our way. If it hits Earth, it might not just kill a city. It could kill a whole region.
I wouldn't exactly want to be there when that happens. I want to be very, very far away.
Apophis will skim Earth in 2029. But its path could change, possibly turning a future miss into a direct hit. April 13th, 2029. A speck of light races towards the Earth. It's an 1,100-foot wide asteroid called Apophis. We are about to have an extremely close shave.
It's the closest approach of any asteroid that didn't actually hit us for a long, long time. It will be 10 times closer than the moon itself. It'll be so close, it'll be brighter than some stars.
The football stadium-sized Apophis will race over the Atlantic.
If it were sitting on the surface of the Earth, it would weigh about 50 million tons, something like that. And that is not the place you want it to be. You want it to be in space and far away.
When we discovered Apophis in 2004, we thought it might be on a collision course with Earth, with a potential impact greater than the largest atomic bomb ever exploded.
The largest nuclear device, atomic device ever detonated on our planet was the Tsar Bomba bomb in Russia. This is something like 55 or 56 megatons. When Krakatoa exploded in 1883, that was something like 200 megatons. Apophis impact would be 450 megatons. If something like that were to happen over New York City or Washington, D.C., you're going to lose the city.
The impact would be at least 10 times greater than the simulated asteroid strike on New York.
Well, when you put it in those terms, that's just plain scary.
In a word, an impact from an Apophis-sized asteroid would be bad. Very, very bad.
Apophis's orbit will cross Earth every 7 years this century. It won't hit us in 2029, but this close encounter could change Apophis's orbit.
When a small asteroid encounters a bigger body like a planet, it's like a bunch of roller derby players. Most of them are clumped together, but maybe there's one just on their own particular orbit. And as they circle around, as they get close to that larger clump, there'll be some interactions, potentially violent interactions, that will change the future trajectory of that lone roller derby skater. And the next time around, it might be a wide miss, or it might be a head-on impact.
It's the same in the solar system. The combined gravity of the Earth and Moon creates what's called a gravitational keyhole, a gravitational sweet spot, which could change Apophis's orbit.
That will change the potential future trajectory of this rock and might make it totally harmless, or might increase the chances of an impact even further in the future.
Because of the gravitational keyhole, there's still a small chance that Apophis will hit Earth in 2068.
That is the important lesson that Apophis taught us. You can miss the Earth, but if you pass through one of these keyholes at some time later, you will hit the Earth.
We now know Apophis will miss the keyhole in 2029. But there are other keyholes and other close passes. Apophis is not a lone threat. There are an estimated 832,500 asteroids orbiting the Sun.
Most asteroids live their lives perfectly peacefully past the orbit of Mars or trailing Jupiter and don't mind anybody else and don't cause any troubles. But some asteroids are on very particular orbits that cross the orbit of the Earth.
These asteroids have left the stable orbit of the asteroid belt and moved into orbits that get near our own. These asteroids are called near-Earth asteroids, or NEAs for short.
The near-Earth asteroid population is interesting and potentially dangerous because they're the ones that actually cross the orbit of the Earth. So they're most likely to have, at some point in the future, an impact with the Earth.
Most NEAs pose little or no threat to Earth. But we've detected over 2,000, including the 1,200-foot Apophis, that do. These are called PHAs, potentially hazardous asteroids.
The difference between a near-Earth asteroid and a potentially hazardous asteroid is distance and size. Anything can get near the Earth, and that could be 20 million miles away, something like that, and be a near-Earth asteroid. But a potentially hazardous one can hit us, and it's big enough to do damage. So something that over the next 100 years or so has a chance of hitting us and doing damage when it does, that's a potentially hazardous object.
PHAs are asteroids that are 460 feet or larger that could collide with Earth.
Take a 400-foot asteroid. If it hits, it would release as much energy as 3,000 Hiroshima nuclear bombs.
In July of 2018, NASA published a map of all the known NEAs and PHAs. The animation tracks their discovery from 1999 through 2018.
Every time I look at this animation, it does make my heart stop a little bit because it looks like we're in the middle of this swarm of angry bees circling all around us.
In 1999, we'd identified under 300 NEAs scattered through the inner solar system. 10 years later, we'd found 500 more. By 2018, we'd discovered 18,000 near-Earth asteroids, but we estimate there are millions out there.
It seems like we could never find all the asteroids. They just keep coming. It's like we're fighting an army of zombies.
Zombies that keep hurtling our way, hitting the Earth at up to 64,000 miles an hour.
That is very, very fast. That is much faster than a rifle bullet. And that's the key to its destructive power.
When a really fast and really large asteroid hits, the impact is off the charts. The blast is so intense, it can melt or even vaporize rock. January 2019. A total eclipse of the moon. Astronomers train their telescopes on the darkening lunar surface. They capture a bright flash that lasts around a quarter of a second.
It was recorded. There were a lot of live webcasts and things like that going on at the time. And you can see this flash of light.
What the heck was that?
At first, the cause of the flash was a mystery.
It turns out it was actually a meteorite hitting the surface of the moon. And because it was dark, and because we were all looking at it, we could actually see it.
The moon's dark surface gave us a unique view of what happens when an asteroid strikes.
What was so exciting about being able to see this impact on the moon in a dark area is that we could actually look at the light that it produced and then back calculate exactly what the size of the impactor was.
We worked out that the impacting asteroid was just 20 inches wide. The crater it blew out was 45 feet across. How can something so small be so destructive?
The two things that matter the most are how fast it's going and how massive is the thing. The more massive, the bigger the boom. The faster, the bigger the boom.
Speed and weight are two very important factors to assess how much damage an asteroid will do. Just like a boxer, if a tiny person like me were to swing a punch, it would do a lot less damage than a heavyweight champion.
Same thing with asteroids. The bigger they are, the bigger the punch. But the same thing is fast, right? If I hit you really slowly, it's not going to hurt. I have to really wind back and pop. That's what happens with an asteroid.
The damage from an asteroid strike is determined by its kinetic energy. Kinetic energy depends on two things: speed and weight. Of the two, speed matters most.
If you double the mass, you double the kinetic energy. But if you double the velocity, you get 4 times the kinetic energy.
3 times the speed, 9 times the impact energy.
10 times as fast, it has 100 times the energy. So the velocity is what's really critical here.
The lunar asteroid weighed only 100 pounds, but it was traveling at 38,000 miles an hour, carrying a huge kinetic energy, which gouged out the crater. It's the same principle for impacts on Earth. 50,000 years ago, a 150-foot asteroid hit what is now Arizona. The impact blasted out an impressive hole, now called Barringer Crater.
It's about 3/4 of a mile across, over 500 feet deep. You could put the Washington Monument in the bottom of the crater, and the top of the monument wouldn't quite clear the rim. It's a pretty impressive hole in the ground.
In 2016, impact specialist Kathy Plesko visited Barringer Crater to see firsthand what mass and speed do to the surface of the Earth.
This is awe-inspiring to stand on the rim of a crater like this, understanding just how much energy it must have taken to excavate this much rock. An asteroid came in at about 27,000 miles an hour. It comes slamming into the surface and just explodes. anywhere nearby here would have seen winds of thousands of miles an hour as the shockwave came out.
The immense power of an asteroid impact comes from the kinetic energy being transferred from the space rock into the surface rock.
It's an extremely violent process, and it starts with the moment of contact of the projectile with the surface itself.
It pushes into the crust, and at first it's just almost punching like sticking your thumb into dough. It's only about as wide as the object is. It's going straight down in, but then it's meeting resistance from the surface of the Earth. And so it squishes until it runs out of momentum, but then it's very compressed, and all of that energy is in a very small space. As it releases, it detonates like a bomb, and that's what makes the impact crater.
Simulations of an asteroid strike in the lab reveal the impact in slow motion. As the high-speed pellet hits the surface, the sand compresses downwards, then rebounds.
And as that rebound is occurring, that's when the material is being ejected out of the crater itself. You'll see the surface erupting outwards like the blooming petals of some big rocky flower as all this debris goes spraying out in every direction.
The 150-foot Barringer asteroid turned the rock to powder. 66 million years ago, an asteroid around 200 times larger and moving 1.5 times faster than Barringer hit Earth. This asteroid impact, called KPG, had so much energy it turned rock to liquid.
This thing was immense. It's really hard to wrap your head around just how big it is. When it hits, the back end of it is so far back that it's where a modern jetliner would fly.
The KPG asteroid hit the ground with a lethal combination of mass and speed. 1 trillion tons, traveling at 45,000 miles an hour.
Some rock is completely vaporized. It just becomes a gas. You have some rock that it's melted. You have some that's thrown out into space.
This material goes up through that and then falls down and settles down over a huge area. That might be dust, it might be pulverized rock, it might be vaporized metal. It's all of this hot material raining down everywhere.
Some of the rock exploded skywards, but rock below the surface was slammed by a shock wave that was completely off the charts. Rock stopped behaving like rock.
We experience rocks as solid objects, but if you hit a rock hard enough, it flows like water.
The KPG asteroid hit so hard, it pulverized the rock, turning it into liquid.
Almost like ripples on a pond moving away from a stone that's been dropped in it.
It's almost like a splash in the solid body of the Earth itself. And like a water droplet splashing in water, you'll see that central peak will kind of splash up and rise to a high altitude and then come back down again. We think a process very similar to that probably happened in the rock itself at the center of the crater, rising up as high as the Himalayas before relaxing back down into their current position again.
The material slumps, and so these ripples are frozen in the rock. And there are other fragments that go away radially, almost like the spiderweb pattern in glass that you get after it's shot with a bullet.
The KPG impact blew out a crater 111 miles wide. It is the third largest confirmed impact structure on Earth. A large and fast asteroid heading our way is always going to be a problem. So, what do we do? Wait for oblivion? Or fight back? The space in the inner solar system seems calm, stable, and empty. it's not.
There are tens of thousands of near-Earth objects just whizzing around Earth.
Now, space is big. They're not going to hit us every time they orbit the sun, but this does set up the possibility that one of these years, we're going to end up at the same spot in space at the same time as that asteroid, and then it's going to be an impact.
We're living in a cosmic shooting gallery. Asteroids strike the Earth all the time through history, and it's going to happen again.
Scientists are developing strategies to stop an asteroid from hitting our planet. Our options? Destroy or deflect the space rock. But first, we need to detect any dangerous asteroids heading our way.
It's a little bit unnerving to know that we haven't yet detected all of the asteroids that exist that could possibly cross our path.
We've discovered a lot of asteroids now, but we typically discover the big ones. But for asteroids that are below 100 feet, there's a lot still out there that we haven't discovered. And such an asteroid can do some real damage if it were to explode over a populated area.
To prevent such a catastrophe, we need to find all asteroids whose orbits cross our own.
Detection is crucial in our defense against asteroids. And the reason is, the earlier they're detected, the easier it is to deflect them away from hitting the Earth.
You want to do deflection, the first step is detection.
The problem is, asteroids are very hard to detect.
Finding asteroids and cataloging all of their orbits is really challenging. They can move quite fast across the sky, and they might go away on the other side of the sun for years and years and years.
So, we can't see them. And even when they are on this side of the sun, they're hard to spot.
But the problem is they're very small and they're very dark. And when I say very dark, I mean really dark, like a lump of coal. So how do you find a small, dark rock just wandering around out there in the solar system?
The Catalina Sky Survey has the answer. The huge telescope in the mountains above Tucson, Arizona, takes a series of images over a 20-minute period. It's hunting for anything that moves. Because stars don't move, but asteroids do.
If it's a really bright asteroid, we will see some bright points of light tracking across the four images. Ah, here we go. This is a real object. You can see it's moving across the sky here from the lower right to the upper left. We are very, very excited to have discovered one tonight because this is an object that's approaching near Earth space, likely in the neighborhood of Earth.
Catalina has limitations. It can only see visible light, so a particularly dim asteroid could be missed.
Asteroids are very cold. They're usually quite far away from the sun. But amazingly, the best way we have to find these is infrared light. Because things that are cold by human scales can still be very warm to an infrared telescope. So even if asteroids are just a few tens of degrees above absolute zero, that's still enough heat to detect them.
When the infrared space telescope NEOWISE turned its gaze onto asteroids, it had immediate results.
NEOWISE has now detected close to 160,000 new asteroids and comets in our solar system, and about 780 of those are things that are near the Earth.
10 of those near objects have been classified as PHAs, potentially hazardous asteroids. Without NEOWISE, we would have missed them.
Using an infrared space telescope is a way of better detecting some of the smaller asteroids and comets in the near-Earth vicinity.
Detection is an important first step, but it only tells us that there's another asteroid out there.
Once we've spotted an asteroid, all we know is that it's a tiny dot of light. We don't know anything else about it.
So when a new asteroid is discovered, the most important thing is to determine its path, to track it, to figure out exactly how it's orbiting around the sun and how close it's going to get to Earth.
For that, we have to know where they are now, so its current location, and measure how fast it's going and which direction it's traveling. All of these things together are really important for tracking where it's going to be next and whether or not they're going to hit us.
To get this information, we need something much bigger and more powerful. The Arecibo Observatory. Once Catalina, or another telescope, detects a near-Earth asteroid in our cosmic neighborhood, Arecibo's 1,000-foot dish swings into action.
They discovered these asteroids, and then once we know where they were, we can try and point the radio telescope and see where they are at the moment and measure their exact location and their trajectory.
Arecibo achieves this level of precision by using radio detection and ranging, more commonly known as radar.
The planetary radar system at the Arecibo Observatory is the most powerful radar system in the world. We focus on potentially hazardous asteroids, which are those that have a high probability of impacting Earth.
Arecibo sends out radio signals toward the newly detected asteroid.
It emanates radio signals. Some of them hit the asteroid, just like a radar gun from a cop might hit the side of your car.
It was pretty similar, but instead of doing it with a radar gun on a small scale, we're doing it at a really big scale with 1 megawatt power, hitting objects that are tens of lunar distances away.
And then those radio waves bounce back to Earth and we detect them again. And by comparing the differences between what we sent and what we received, we can get a map of the asteroid itself, and we can get where it's moving and how fast it's moving.
Speed, size, and location of strike determine the outcome of an asteroid impact. But the type of asteroid is another factor. It can mean the difference between survival or complete annihilation. The Bering Sea asteroid blew up in the atmosphere, but the Barringer Crater asteroid hit the ground intact with its full force. Why do different asteroids behave differently? And what will Apophis do when it heads our way? Arecibo's radar may have the answer.
When we bounce radar waves off of these objects, we can get effectively imagery of the surface of some of these small objects that we just cannot do with optical telescopes.
This is the radar image of Apophis. It's so far away that all they could image were a few pixels.
So this is our most recent radar image of asteroid Apophis. And you can see it's only a few pixels, but it does give us information on what it actually is.
These few pixels are enough to work out how big Apophis is.
From this image, we can constrain the size to be about 1,000 feet, which is about the same size as the Arecibo radio telescope. All of that from a weird bunch of pixels.
Knowing the size and mass of an asteroid is critical to understanding what an asteroid is made of.
If we have the size and the mass, we get the density. If we have the density, we know what it's made of. Rock has some density, metal has a different density. So we can determine a huge amount about the asteroid simply by pinging it with radar.
Arecibo's data reveals that not all asteroids are alike.
There's not just one kind of asteroid. There are actually several kinds. And this is important to understand because they behave differently. They behave differently if they impact us, and they behave differently if we're trying to prevent them from impacting us.
We need to know what these asteroids are made of if they're going to hit the Earth, because that drastically alters the potential effects.
Asteroids come in different shapes, different sizes, and different compositions. And we think that is because they are the leftovers of planet formation.
To understand how each asteroid formed and their threat level, we have to go back 4.6 billion years to the start of the solar system.
The reason that there are all these asteroids floating around in our solar system today is just because of the early violence of the solar system as it was forming.
At the birth of the solar system, the sun ignites, leaving a disk of gas and dust. Slowly, over time, planets form. Lots of planets.
The early solar system was a messy place. There were a lot more planets, a lot more forming planets. They would crash into each other, they would merge, they would disintegrate, they would reform.
This process of accretion, of building planetary worlds, was not just, kind of gentle and happy. It was violent.
It was like a giant cosmic game of pool, planet smashing into planet. The leftovers from this violence formed a ring of junk between Mars and Jupiter.
And now we call that junk asteroids.
They're just basically rubble left over from the formation of the solar system.
Rocky leftovers became C-type, or chondrite asteroids. They're quite dense, so big ones can punch through the atmosphere and hit the ground. Radar reveals a rarer type of asteroid.
Some of them really stand out because their density is so much higher than the rest of the other asteroids.
These asteroids are M-type, or metal. Because their mass is great, they carry more kinetic energy during a strike.
By far the worst one is this iron meteorite. This is really heavy. So the difference, if you were being hit by this, it would be the difference between being hit by a rock and being hit by a metal hammer.
We think that both the Barringer and the KPG dinosaur killer were caused by metal asteroids. But there's another, more mysterious type floating through space. December 2018, NASA's spacecraft OSIRIS-REx approached the near-Earth asteroid Bennu.
Over time, it drifted out of the main asteroid belt, made its way into the inner solar system until it became a near-Earth asteroid accessible for our spacecraft to go and visit.
OSIRIS trained its camera on Bennu.
One of the biggest surprises on arrival at Bennu was the large number of large boulders on its surface. Bennu is really littered with huge boulders and littered with medium-sized boulders and littered with small boulders.
Bennu is not a solid lump of rock. It's made up of thousands of bits of rock forming what we call a rubble pile.
These asteroids aren't big singular spherical balls of rock, but rather they're literally piles of rubble. There are all sorts of pieces and fragments from another asteroid that had previously been disrupted that have all come back together and formed literally a pile of rocks, held together by their own gravity.
We think rubble piles formed from collisions inside the asteroid belt. Each impact blasted bits off. Then, over time, they came back together to form a loose pile of rocks.
Imagine taking a big cosmic dump truck full of gravel and rubble and dumping it out there into space and letting gravity weakly hold it together.
When scientists probed deeper into Bennu, they found another surprise. It's full of holes, like Swiss cheese.
If you could slice open one of these asteroids, you'd see there are a lot of voids. And in fact, 60% of what we're looking at is a void space. So they're actually really fluffy. So even though they're made of rocks, they're sort of the lint of rocks.
Bennu helps us understand Apophis. Radar data shows that Apophis is also a rubble pile.
If you look at Apophis, we really want to know how its orbit will evolve in the future. what we learn at Bennu about similar-sized rubble pile asteroids might help us understand the future of an asteroid like Apophis.
So what would happen if the rubble pile called Apophis hits Earth?
You probably don't want that to hit you still, but it definitely makes it a lot weaker than something like a solid rock, or even more, a chunk of nickel iron metal.
Does its composition make it any less of a threat?
A rubble pile like Apophis is especially unnerving because we don't know when it interacts with the atmosphere if it's going to stay as one solid piece. Will it break up?
When these rubble piles start interacting with planets, if they fly near a planet, they can get pulled apart into all of their little pieces. Or if they enter the atmosphere of a planet to impact the surface, they might slowly get pulled apart as they enter the atmosphere and end up being an array of little impacts instead of one big single impact.
But what would happen if these impacts occur at sea? Will our oceans save us, or will a giant tsunami wipe us out? In 2019, U.S. researchers discovered deposits of fossils. They contain both the remains of land and sea creatures.
You see things that are all jumbled together. So you'll have fossils of sea creatures, you'll have ocean deposits that are mixed up with coastal deposits and onshore deposits. And you see those deposits in places that are very, very far away from where you would expect them to be. And so this material was obviously thrown very far inland.
The jumbled deposits suggest that the creatures were killed at the same time, in a huge and violent event. Something powerful enough to sweep ocean-dwelling creatures far inland. A tsunami. Tsunamis are usually created when the ocean floor moves suddenly.
The ground picks up the entire ocean and shakes it up and down. And it's sort of like taking a rope and shaking it. And it moves all across the ocean floor and ocean surface until it reaches land.
The biggest recent tsunami was caused by the Earth's crust at the bottom of the ocean lifting slightly. So this means that that entire length of crust that lifted displaced the water above it. So the waves, the tsunamis that result, are really long and wide, and it can travel across the ocean at tremendous speeds and up on land.
Is this what happened to the fossilized creatures? Were they killed by a huge tsunami? Clues come from dating the preserved remains. They're 66 million years old. From the same time, a 6-mile-wide asteroid crashed into the sea off the Yucatan Peninsula in Mexico. Are the two events connected? Do ocean-impacting asteroids trigger tsunamis?
We used to think that a big asteroid impacting in the ocean would drive a tremendous tsunami, a huge wall of water, out at very rapid speeds, which would basically scour clean everything.
Now, new research from 2018 suggests a very different scenario. Scientists use supercomputers to model asteroids hitting the deep ocean to work out how much of the asteroid's kinetic energy is converted into a tsunami. In the simulations, a 1,600-foot asteroid hits the ocean at 20,000 miles an hour and dives into the water.
As it goes deeper in, of course, it's meeting a lot of resistance, and it slows down and it compresses up. It compresses and compresses and compresses. And then finally, it runs out of momentum, and it's at an extremely high pressure.
The huge pressure causes the asteroid to vaporize. Temperatures hotter than the surface of the sun turn trillions of gallons of water into steam. The blast creates a huge, short-lived cavity in the water's surface and a splash curtain a wall of water that leaps up several miles. This curtain then collapses and water falls back into the cavity, shooting a column of water 5 miles up.
This very tall column can't support its own weight and collapses back down.
The collapse of so much water triggers a wave 1,200 feet high. Could this become a huge tsunami?
If we think about a meteor striking the ocean, we want to understand how far the waves might propagate from this site. We could actually just use a stone and throw it into a pond. And you might think, okay, well, it's a big stone, it's going to make a really big splash, and that's just going to extend out a long distance. But it turns out the splash stays the biggest, really close to where it impacts, and then the ripples die down after that. So let's try that. Big splash in the middle. And we see the ripples going outward, but they're really pretty small compared with that initial big splash.
It's the same with an ocean impacting asteroid. The impact creates surface waves that die away quickly because only a small amount of the asteroid's kinetic energy gets into the water.
It's actually pretty tough to make a tsunami like that. The energy of the asteroid doesn't couple well with the water to drive this wave. Instead, most of the energy goes into vaporizing the asteroid itself, as well as all of the water around it.
Only 1% of the asteroid's kinetic energy goes into making a wave. So, only low-energy waves form, too weak to become giant tsunamis traveling hundreds of miles. So what caused the jumbled fossil deposits found thousands of miles away from the impact site?
We don't think there could be that much energy still transmitted that far away from the impact site. Instead, there has to be a different source of energy that created different waves right about the same time as that impact event.
Research from 2019 may have the answer. The KPG asteroid struck on the continental shelf, the shallow region between land and deep ocean. The impact triggered a localized tsunami, large enough to kill creatures in the region. But it also sent a huge shock wave into the bedrock.
There's going to be a shock wave driven through the ground. That probably would have killed anything in the area.
If you had a dinosaur that was standing on the Gulf Coast of what is now the United States, that animal would have experienced a seismic pulse, an earthquake, that is stronger than anything on our current Richter scale. It would have actually driven its legs up into its body cavity, killing it instantly.
There's all manner of mayhem and death taking place at this time. There was no escape in this event.
The initial shock wave smashed into the ground rock and traveled through the Earth's crust.
The impact would have shaken the crust of the Earth, which also would have triggered earthquakes around the world, which themselves may have triggered secondary tsunamis.
Secondary tsunamis, thousands of miles from the impact site, killed both land and sea creatures. The KPG impact went on to wipe out 70% of all life on Earth. So how did one asteroid strike cause a global kill zone? "66 million years ago, 70% of life on Earth died after the KPG asteroid strike. How could one space rock hitting the sea cause a global catastrophe?
When you have a big rock hitting the ocean, the biggest danger is not from the waves, but actually from the steam that it creates.
The impact vaporized trillions of tons of seawater. This steam rose up into the atmosphere, where it condensed into water vapor.
Water vapor is a greenhouse gas, so that's then going up into the upper atmosphere, and it's trapping heat, but at different layers it's making clouds. It's just throwing everything off kilter.
Water is a very effective greenhouse gas. So you will actually affect some very significant climate change very quickly as a result of that impact.
Within weeks of the asteroid strike, water vapor in the atmosphere caused temperatures to rise. But that was only the start. The impact also blew out 10 trillion tons of rock, ash, and dust.
This asteroid is so big, 6 miles wide. It's punched a hole in the air. There's like a column of low density, a chimney, that goes from the ground up to the top of the atmosphere. And that means there's very little air resistance in that tunnel. These rocks can actually blast up into the chimney and find it easier to get up out of the atmosphere.
It sent that material flying up halfway to the orbit of the moon, circled around the Earth, all this ring of material falling back onto the Earth, and it was like the sky itself was on fire.
So not only do you have rocks falling on you, but they're molten. And these rocks will start catching plants and anything else on fire.
Soot and ash rose into the atmosphere, blocking out the sun.
Material was thrown into the atmosphere, plunging the planet into a nuclear winter. It was complete chaos, and it went dark for 2 full years.
Without sunlight, temperatures dropped. Just months after the impact, the planet cooled by 20 degrees.
In the immediate area, there's just tremendous destruction. Just everything gets destroyed. But over the long term, you're talking about ash kicked up in the atmosphere, extremely cold weather, basically a global ice age.
The freezing temperatures killed off most plant life.
Imagine how that affected life on Earth. No plants, and the base of the ecosystem collapses.
This dark nuclear winter lasted 2 years and prevented plants from photosynthesizing.
So if plants can no longer use photosynthesis to live, they'll die. And then with no plants, then you have no food for these larger animals. And so anything that eats those animals will also die. If you lose your plants, you're going to lose your large-scale life.
First, the plant-eating herbivores died off, followed by the meat-eating carnivores.
Most of the dinosaurs were just unable to find food and to survive through the cold, long night.
The global devastation wasn't over yet. The rock of the continental shelf where the asteroid hit contained carbon and sulfur.
These carbonate rocks were heated and vaporized and released carbon dioxide into the atmosphere, yet another greenhouse gas.
So you're vaporizing a lot of sulfur, a lot of salts of different kinds that are then lofted up into the upper atmosphere that then plays havoc on the climate.
These greenhouse gases built up in the atmosphere, forming a warming blanket, triggering the next phase of destruction. Global warming on steroids. Temperatures rose 10 degrees above normal. Then the oceans warmed as well. Oxygen levels dropped, and the seas became toxic to simple life forms.
It actually made it impossible for certain microbes to actually live, and they're the basis of the food system. So really, it changed what could actually live in the ocean and how much could live there.
Dead zones appeared in the oceans, just as they had on land. Nearly 3/4 of all life on Earth died. All from one asteroid impact. To prevent it from happening again, we need to track all potentially dangerous asteroids. But that isn't easy, because these space rocks can change direction. Sarıçıcak, Turkey. Security cameras record a flash in the sky. The flash? A 3-foot asteroid exploding in the atmosphere.
It blew up in the atmosphere and rained down. And people saw that, it was very noticeable, and they went and they collected those meteorites. And then they tried to figure out what they were looking at.
The debris was sent for fragment analysis.
I have a piece of one here. So first, on the outside, you can see it has a really black fusion crust. This is from when it fell into the Earth's atmosphere, so it was melted. But when you look on the inside, it reveals this beautiful, very light-toned, fine-grained material. And so these meteorites are incredibly distinctive and really beautiful.
The meteorites are rocky. Their beautiful color comes from a mineral called howardite. It's rare, and it doesn't form on Earth.
Howardite meteorites come from the asteroid Vesta, and we know that because of the Dawn mission that actually went to Vesta and took a look at it very carefully, so we know the composition very well. And so now suddenly here was a new kind of meteorite that's in Turkey that matches the Vesta family of meteorites.
But how can we be sure that these bits of space rock came from Vesta, an asteroid over 100 million miles away?
It was a fall meteorite, and so what that means is that someone saw it. We saw it fall, and so we knew its trajectory, so we could actually work backwards to say, where did that meteorite come from?
Retracing the trajectory of the Turkish meteorites took the scientists all the way back to the 328-mile-wide Vesta. When they studied Vesta's surface, they found further evidence.
On the surface of Vesta, there's actually a very large and fresh impact crater that is around the same age of the Turkish meteorite. So that really clinched it. This thing is definitely from Vesta, and we proved it.
So how did bits of Vesta end up here on Earth?
22 million years ago, some very large impactor struck Vesta and made a huge crater. And some of the rocks from that crater actually escaped from Vesta's gravity and were lofted into space.
Some of these rocks from Vesta went into orbits that intersected with Earth. 22 million years later, one blew up over Sarıçıcak. The Sarıçıcak meteor shows that the asteroid belt is an unstable environment. Asteroids frequently strike other asteroids.
That's actually happening all the time. Things are running into each other in our solar system right now. And so that makes it really hard for us to track all of those objects because we don't actually know what happens after they collide with each other. Now things are totally different, and that changes the whole system.
Each collision makes more asteroids.
There's many different possibilities of what could happen when asteroids collide. Imagine a roller derby situation. If you have two groups of players that run into each other, that could be like two asteroids running into each other. And one possible outcome is that one stays intact while the other is completely blown apart.
That sends fragments flying all through the main asteroid belt. And then those little asteroid fragments are on their own independent orbits around the sun.
A problem with asteroid impacts is that we're always making new asteroids. There are big asteroids out there, and they get hit by other asteroids, and then you get shrapnel. And now you've got not one big one and one smaller one. You've got one big one, one smaller one, and millions of little ones. Now, most of these aren't very big, but some of them might be bigger and could be potentially hazardous.
As the solar system ages, the number of asteroids increases. Each new space rock travels on a new course, which could intersect with Earth.
So we're constantly producing new asteroids and big collisions in the main asteroid belt. And these are producing the small asteroids that will eventually drift inward in the solar system.
Tracking this constantly evolving population of asteroids gives scientists a huge headache.
If they break apart, then that gives you even more pieces of the asteroid to track.
It's not a simple thing to track and predict the orbits of asteroids and their movements, because one tiny little change can have huge dramatic impacts for its possible future.
Figuring out exactly where they're going to go and keeping track of how they interact with each other, this is a huge endeavor.
The sheer volume of asteroids can affect the behavior of other asteroids as they gravitationally interact.
Think about your roller derby player, skating in circles. The path they're going to follow would evolve the more people you plop down on that track. They start interacting with each other and their trajectory will change. The more crowded you make the solar system, the more things there are to change your orbit of your individual asteroid.
It's not like air traffic control where there's a known amount of airplanes and they all follow a plan.
This situation is further complicated because asteroid orbits can be affected by other, more subtle forces.
One of these is called the Yarkovsky or the Yorp effect. Honestly, Yorp is more fun to say.
The Yorp effect is caused by sunlight hitting an asteroid.
Light is made up of photons that are traveling, and these photons actually have momentum. So when light shines on something, it actually pushes on it.
When sunlight hits an asteroid, the photons give it a tiny push, enough to change the space rock's trajectory. When we know an asteroid is really heading our way, it's time to fight back.
So we've got an asteroid that's headed at us. What do? Two main possibilities. We deflect it, we nudge it a little bit so it misses, or we blow it up, we destroy it. Which of those do you want to do?
It's a tough choice. Get it wrong, and we could end up being hit by a swarm of radioactive space rocks. An asteroid is heading our way, and it may hit us in 2068. How do we prevent such a catastrophe and stop it from ever getting close?
Well, you just don't want it to get anywhere near us in the first place. So what do? Well, you can destroy them, or you can push them out of the way.
This is something where our science fiction ideas have gotten it almost entirely wrong.
If you're in a bad movie, a really, really bad movie, you can send astronauts to an asteroid, put a nuclear bomb in it, and blow it up into lots of little bits that then burn up harmlessly in our atmosphere. Yeah, it doesn't work that way.
Blowing up an asteroid would make the problem much worse. We're no longer dealing with just one space rock.
My issue with this is that you may have turned one problem into 50. Instead of one regular-sized asteroid, now you have a whole bunch of littler ones, and these may still hit the Earth and cause damage.
And you know what? That's not much less fun than just having a single big asteroid.
Now you've just taken all that devastation and spread it out for everybody to enjoy.
The problem with using a nuclear device is that the products that rain down on Earth are now radioactive.
If a dangerous asteroid was on its way, blowing it up would be a last resort. A less risky method is to deflect it off its collision course. A small nudge, early enough, can change an asteroid's trajectory away from Earth.
You don't have to nudge it very much for it to miss, right? So if it's headed straight at it, I just touch it slightly. By the time it gets to Earth, it's way off course.
NASA is investigating ways to change an asteroid's path, including using a nuclear burst.
In a nuclear burst, what we do is we don't actually hit it. We come up to it with this device on a spacecraft, and then the device would be detonated at a certain height above the surface.
That heats up the surface of the asteroid, which vaporizes. You get vaporized rock or metal, which blasts off the surface, and that's how a rocket works. So you blow up a bomb here, and it winds up pushing the asteroid in the other direction.
To prevent any potential nuclear fallout, NASA would detonate the bomb a long way from Earth.
Any deflection attempt has to be done years in advance, which means it would be done on the other side of the solar system from us, on the opposite side of the object's orbit. That means that all of the vapor made during the explosion gets blown away by the solar wind.
NASA is investigating other, less explosive methods of deflecting an asteroid. D-Star would blast the asteroid with a laser.
We hit it with the laser, material vaporizes and flies off the asteroid, and because of Newton's third law, which is that for every action there's an opposite and equal reaction, this means that vaporized material moving off in one direction moves the asteroid in the opposite direction.
Both the laser and the nuclear burst are still just ideas on the drawing board. But one asteroid deflection mission, called Double Asteroid Redirection Test, or DART for short, is already up and running and scheduled for launch in 2021. DART is a kinetic impactor and will try to knock an asteroid off course.
At NASA, for the longest time, all we've been able to do is theorize about how we change their path. But now, for the first time, we're actually going to practice it.
Leading this groundbreaking mission to bump an asteroid off its orbit is Dr. Andy Chang.
DART is the first planetary defense mission that we've ever done, where we take a spacecraft, we fly the spacecraft into the asteroid to change its course and make it miss the Earth.
DART's target is a 525-foot space rock orbiting the large near-Earth asteroid Didymos.
We picked the near-Earth asteroid Didymos as a target for the DART mission because although it's a near-Earth asteroid, it's one that's very safely parked away out there in space. There's no way we can move Didymos or its moon in any way big enough to cause a problem for the Earth.
The Didymos asteroid weighs around 10.5 billion pounds. So how do you knock such a large lump of rock off its path? We're sending a spacecraft to knock the Didymos asteroid off course. The asteroid is moving at over 36,000 miles an hour and is around 7 million miles away. So, how do you move a 10.5 billion pound space rock?
You need to hit it really hard to change its orbit. So it's going to be coming in at a super high velocity in order to impart a bunch of energy and momentum to that moon.
DART will hit the target at around 14,000 miles an hour.
The speed of the DART impact will be more than 9 times the speed of the rifle bullet from an AK-47.
The impact will give the asteroid a small push. To work out how big a push, we test impacts with the Ames vertical gun.
At the NASA Ames Research Center in California, there's a very special facility called the Ames Vertical Gun Range. It's a hypervelocity gas gun that allows us to shoot little metal BBs at rock targets at speeds up to like 14,000 miles per hour.
The gun replicates the impact the DART mission will make. It reveals that an impact will blow off a small amount of debris, but at extremely high speed, enough to give the asteroid an additional kick.
The impact will blow off pieces of the asteroid. So the pieces are thrown off the back, and so that process acts like a little rocket engine.
That provides an additional momentum change, momentum push to the target itself.
The combined push from the kinetic impactor and the ejected debris is tiny, around 9/10 thousandths of a mile per hour. But hopefully, it's enough to change the asteroid's orbit If DART works, we could then use a similar mission to defend Earth when the time comes.
This isn't some small rock prototype that we're doing this test on. This is a real dress rehearsal for an asteroid that could destroy cities or even maybe send the Earth in chaos.
The moon of Didymos is a solid lump of rock. Will a kinetic impactor like DART work with a rubble pile asteroid like Apophis?
When you shoot a rubble pile with a projectile, it's a little bit more like trying to punch a sandbag. You get a lot more of the energy is absorbed into just moving the sand around inside the bag than ejecting it. And so rubble piles might be a little harder to move by this method.
We don't know if we can deflect a rubble pile asteroid like Apophis. They remain a clear and present danger, and something we might not survive. But there may be a space lifeboat. In 2018, scientists re-examined rocks collected by Apollo 14 astronauts from the moon. Buried in the samples was a rock that shouldn't be there.
They got something they didn't expect, and that was an Earth rock. They actually picked up a rock from Earth on the moon. They didn't bring it with them. It's very likely that it was something that was lofted up when something hit Earth, threw up a bunch of rocks. Some of those rocks fell onto the moon. And that's a meteorite on the moon, but it's from Earth.
Supercomputer simulations of the KPG asteroid strike reveal how the impact had so much energy that it catapulted rocks out of Earth's atmosphere and into space. They were then caught by the moon's gravity and pulled down to the lunar surface. We now know that material ejected into space from asteroid impacts can travel to other planets as well, which would explain the 100 Mars meteorites we found here on Earth.
We think that there was probably the exchange of a huge amount of material between different bodies, Earth to the moon and back again into Mars.
With each impact that occurs in our solar system, that ejects all types of material that allows material to swap from planet to planet, moon to planet, moon to moon. And so there's all of this material that eventually travels from place to place.
Should another giant asteroid hit our planet, this planetary interchange may give life on Earth a lifeline.
If you think about such an impact today, the chances are high that a lot of life will be wiped out. Much of life, probably all of human life.
It's certainly possible that a big enough asteroid strike could completely sterilize a planet. Talking about no life whatsoever.
Not to put too fine a point on it, but if there's a dinosaur killer asteroid out there and it hits the Earth, the chance of humanity's survival of such a thing as a species, not great.
Humans may not survive, but some scientists believe that simple life forms could. Asteroids have hit our planet many times in the past. One giant strike wiped out 70% of all life on Earth. If another huge asteroid hits us, can life survive?
If a giant rock hits the Earth and kills almost all life on Earth, there is a slim line of hope. And that's because the dirt, the rocks on Earth are infused with bacterial life, with microscopic life. And in the event of a giant impact, some of these bits of rock will be ejected into space. and might float around.
After an asteroid impact, whatever ejected into the atmosphere could contain microbial life that, when it falls back down onto the ground, could reseed the life on that planet.
Some bacteria can survive the harsh conditions of space and can cope with an asteroid strike, re-entry, and landing back on Earth's surface.
I think in terms of life on planet Earth, I think we've learned that we live on a very resilient planet. And I think life in some form, even if it has to crawl its way back from bacterial stage, I think life on this planet is going to eke through.
Life is pretty good at figuring out a way of surviving. We know that life first formed on the Earth well over 4 billion years ago and has never been wiped out in all of that time. There's always been something after every major mass extinction. So life will continue. It just won't necessarily be us.
An asteroid strike on another world may be how life on Earth started in the first place.
There's an interesting idea that an asteroid strike on another planet could have actually seeded life on Earth. And the way this works is you have life that's somehow gotten a foothold on some other planet like Mars. A big asteroid strike hits that planet and knocks a piece of it off, eventually rains down on Earth, carrying with it life.
We may owe the existence of life here to asteroid impacts. That's speculative, but it's kind of a cool thought.
Life-seeding asteroids may have hit us in the past, and other asteroids will hit us in the future. One of those may be Apophis, arriving in less than half a century. Maybe we'll deflect it. Maybe it'll miss us all on its own. Either way, we need to keep tabs on it.
The best thing we can do as a species, and it's funny because it almost sounds like I'm advocating for more jobs for astronomers, we need to keep looking at the sky. We need to look at the sky longer and deeper with more sensitive instruments and get more of a sense of what out there is around us. That's what our species needs to do to ultimately survive.
Because now we have the ability to see these things a little bit better, we have the ability to protect ourselves better. It doesn't have to be a surprise. You know, the first time we see a big impact doesn't have to be as it's bearing down, destroying our planet. We can actually see it before it gets to us and decide what we want to do about it.
Earth's history is littered with asteroid strikes. Some wiped out millions of species. Some may have seeded life in the first place. What the future holds in our relationship with these space rocks, no one knows.
Even though the chances of something really large hitting the Earth are pretty small, the consequences are dire. It would really destroy our planet, or at least life as we understand it. And so in many ways, asteroids are the greatest threat that we face.
Life is fragile. So of course, we live in a larger environment where something could come and hit us at any time. That's part of being alive. There's no guarantee tomorrow will happen. But what there is a high likelihood that you'll still be safe tomorrow.
Impacts from space are rare, but if they do happen, it's a huge deal. And so you got to put those two things together. That means we got to pay attention.
Those impacts have happened many times in the past, and they're going to continue to happen many times in the future. Fortunately, it's not probably in our immediate future.
Impacts are rare, but the Earth lives a long time. So you're unlikely to get in a car accident, but if you drive enough, you're going to get in a car accident.
Over a century timescale, yes, we should be concerned about these. But over the daily, weekly, monthly, even yearly timescale, I wouldn't sweat it too much.
I wouldn't say we should lose sleep over an asteroid or comet striking Earth, but the reality is it will happen again.
So when you think about asteroid strikes, remember this wonderful, dramatic universe you find yourself in. We're here because stars died and exploded. Life on Earth wouldn't be the same if we didn't find ourselves in this dramatic and even dangerous environment in space. But this is who we are. This is nothing new. And this will continue for the future of our planet.